Hello everyone, very good morning. I am Lingeshwaran. So I serve in the capacity of an assistant professor in the Department of ECE, St. Joseph's College of Engineering. And today's topic will deal with 5G fundamentals. So even before we get into the topic, so I want every one of you to explore the following provisions. So on your Android mobile, so you go to dialer and just try to type these two things. It's like you can use this short code *#* 4636 ##. So what are the parameters you see on your mobile? The moment you do it, you will get into the Android debugging interface. So this will take you to the Android debugging interface. So what are the parameters you can see with the help of this interface? In the Android debugging interface, you can very well see whether you are using a 4G connectivity or 5G connectivity. And moreover, in case of 5G connectivity, you can also see whether you are using standalone mode or non-standalone mode. So what is the functional difference between these two modes? In non-standalone mode, your RAN part is 5G, but it will be using the legacy 4G core. The core network will be still 4G. What about standalone? In standalone mode, both your RAN plus core network will be 5G. Right? So the basic example for the service providers adopting SA and NSA are, so here for SA we can consider Jio, and for NSA we can consider Airtel. Okay, these are the two major service providers when it comes to 5G provisioning. And here Jio is actually using a 5G core, whereas Airtel is using a legacy 4G core. And moreover, in this interface, apart from the type of connectivity, you can also look at few more parameters, network parameters. So one could be your signal strength. So this signal strength will range between, so this signal strength will be lying between somewhere around, so you will see received power in dBm. So this received power in dBm will be somewhere between -80 and it will be between -110 dBm. Since power is expressed on a dBm scale, you have to know the fact that, so this received power is the right notation that can be used. Okay, so the power level will be somewhere around -80 dBm, and the worst case it could be somewhere around -110 dBm. Okay, received power will range between these two values, right? So this is the actual real-time power what you see on your mobile. Then apart from this signal strength, what are the other parameters you will see? Apart from signal strength, you will see RSRP. This is reference signal received power, right? Then RSRQ, then SNR, right? So say you are using SA mode. If you are using SA mode, you can also see few more parameters like EARFCN, or if you are using 4G, you will see EARFCN. If it is 5G, it is only ARFCN. So what can we interpret from ARFCN? ARFCN stands for Absolute Radio Frequency Channel Number. Okay, so in reality, instead of using frequency as a terminology, here frequencies are converted into a number which is recommended by 3GPP. So they will be using absolute radio frequency channel number instead of conventional frequency notations. Right? Say you are dialing this short code on your mobile, still you are not able to get this Android debugging interface. So now what is the end route to get this interface? If you are not getting this interface directly, what you can do is you can actually download one more application from the Play Store. So from the Play Store, you can actually look for few more applications where you can actually try to explore the existing 5G connection on your mobile. So one such application is Force LTE 4G slash 5G. So you can download this application for free and you can install it on your mobile. The moment you do that, so you will be able to access the same interface where you can witness all these 5G KPIs. So apart from that, I would recommend two more applications available in the Play Store. So one is NetMonster. In NetMonster, you can also see all these parameters in the form of a graph or a SRP or a SRQ, then SNR. So you will see plots for all these parameters, right? So these are our 5G KPIs, key performance indicators. Then apart from that, you can also use GNet Tracklite. So this application is actually power packed if you compare NetMonster and Force LTE. In GNet Tracklite, you can see large number of network related parameters. You can see all these parameters. Apart from that, you can also see what is your G-Node PID, right? And what is your PCI. Okay. Then you can also look at what is your uplink and downlink frequencies. What is your channel bandwidth? Okay. So all these parameters can be witnessed on your mobile. Then you can also see the plots, right? So you can see all these plots. You can also use it in drive mode, right? So many features are available. So I recommend these three applications if you want to understand your current 5G connectivity, right? So now let me get into the basics of 5G. So this is used to study the current 5G connection. Okay. So now let us have a quick overview of evolution of cellular networks right from 1G. Right? So even before we get into the 5G fundamentals, let me start with evolution of cellular standards right. Initially, you very well know people were using analog mobile phone systems, right? And that was nothing but 1G. Okay. And here people were like using only for voice calls. 1G was only devoted for, so this has supported only voice calls. Then people gradually moved to 2G, right? In 2G, we had two different verticals. So one with respect to GSM and the other one with respect to CDMA. So two different verticals, and mainly people focused on TDD slash. People focus too much on FDMA. Okay, along with TDMA also, right? And there is yet another exception. Very few cellular service providers, they were actually sticking to CDMA. Then, so what is the advantage of 2G over 1G? Here people were using, like if you take 2.5G, right? This is basically enhanced data rate for GSM evolution. So here they were able to bring in data connectivity, right? So here, apart from voice calls, they supported short messaging service. Then in 2.5G, people have brought in support for data. So what is the data rate? The data rate was somewhere around 384 kbps. Okay, it's much lesser compared to the state of the art. Then from 2.5G, people moved to 3G, right? So here people used UMTS. Right, these are all standards. HSDPA, right? Universal Mobile Telecommunication System. Here, instead of CDMA, what people use WCDMA, wideband CDMA, right? And they were able to achieve data rates close to few Mbps. This is what they were able to achieve, right? Then small LTE network. Okay, so that is what we call as LTE or simply LTE advanced. Okay, a slightly a bit higher standard compared to LTE. So here, instead of conventional FDMA, CDMA or WCDMA, people have moved to OFDM. Right? So what is the advantage of OFDM? So OFDM, you take a wideband channel, you split that into number of narrowband channels, and this narrowband channel can overcome a frequency selective fading. Right? If at all there is a frequency selective fading, only that particular subcarrier will be impacted, while all other subcarriers will remain unaltered. Then, what is the data rate they were able to achieve? The data rate that they were able to achieve was around, this is around slightly 10 times of it, somewhere around 10 Mbps. Not more than that. I am talking about the downlink data rate. Okay. So then came 5G. In 5G, once again, this is 5G NR. NR stands for new radio. People still retain the OFDMA. But what is the advantage? In 4G, people used fixed subcarriers. Here, variable subcarrier spacings were allowed. Okay. So now, what is the data rate? Here, the data rate was pushed to somewhere around 100 Mbps. This is the downlink data rate. Okay. So that is how cellular standards evolved over the period of time. And if you look at the timeline, okay, there will be at least a 10 years gap between each mobile generations, right? So we are actually looking at 6G in 2013. So this was 2020, 2010, right? And this is 2000, right? These standards somewhere around 1990. Okay, clear? So you could see a 10 years gap between each mobile generation. This 10 years gap is actually this is actually given as a breathing space for the mobile service providers to make a profit out of the investment whatever they have made. So now let us move into the nuances of, let us study the nuances of 5G. So what is the major difference between 4G and 5G? So already we discussed about data rate, right? So data rate, the difference between 4G and 5G, in 4G the data rate was around 10 Mbps, downlink data rate. Here the data rate was around 100 Mbps. And what about latency in 4G? Latency in 4G, it was around 10 millisecond, and here the latency was around only 1 millisecond. Okay, so if you compare these two, we can very well say, right? So 5G is nothing but it is approximately 10x of 4G, right? So this is the interpretation you are supposed to draw, right? The data rate or latency, if you look at these two parameters, so 5G is actually 10x faster than 4G. Then, if we talk about the physical layer, in physical layer, the major difference is in 4G you have only fixed subcarrier spacing. We call it as SCS. It is only 15 kHz. But when it comes to 5G, so we have variable subcarrier spacing. So what I refer by variable subcarrier spacing? Here you are allowed to choose 2 power mu into 15 kHz. Okay, so mu is actually the numerology, or we call it as OFDM parameter. So mu can vary between 0 to 4, right? So in 5G we generally split the frequency ranges into FR1 and FR2. These are the two frequency ranges. So FR1 basically represents frequency is less than 6 gigahertz, and FR2 is basically your millimeter wave. So these frequencies range between 24 gigahertz up to 58 gigahertz. Right? Even though initially people used frequencies between, like initially there was a discussion to include frequencies between 6 and 7.125 gigahertz for cellular, but now FCC has ruled out this decision in favor of Wi-Fi. So now this band is not available for cellular. This is actually available for Wi-Fi 6E standard. Okay, even Wi-Fi 7 makes use of this extended bandwidth. Okay, cellular, it is now only applicable till 6 gigahertz. Right. So now we'll just look at the frame format of 5G. So what is the actual frame format supported by 5G, right? So in 5G, each frame, right? So each frame spans for 10 milliseconds. This is the duration of one frame. Then if you take this frame can be subdivided into 10 subframes, right? And each subframe can be having multiple slots, okay? And these slots are ultimately depending on the OFDM parameter or numerology. So 2 power mu slots will be there. For example, let me take mu equal to 0. Okay, the value of mu is 0. What about 2 power mu? It is simply 1. Right? Now what about the subcarrier spacing? 2 power mu into 15 kilohertz. So 2 power mu into 15 kilohertz will now become simply 15 kilohertz. Right? So 2 power mu, it is only 1 slots. Right? So here number of slots in the subframe will become only 1 slot per subframe. Then in each slot you will have 14 OFDM symbols. Okay, so each frame has 10 millisecond duration. Then within each frame you have 10 subframes. Then what is the idea here? Each subframe spans for 1 millisecond. Then within one subframe you will have 2 power mu slots, right? So the subcarrier spacing is actually decided by OFDM parameter, or you call it as numerology. Based on the numerology, you can actually decide what is your subcarrier spacing and number of slots available within a subframe. Then if you take each of these slots will have 14 OFDM symbols. Okay, so now let us consider the subcarrier spacing to be 15 kilohertz. So what about mu? Mu is actually 0. So 2 power 0 will be 1. So there will be 1 slot per subframe. So now how many subframes are there in a frame? 10 subframes. Ultimately 10 slots will be there. Then how many OFDM symbols will be there? 14 into 10. So you will have 140 OFDM symbols available in a single frame. Right? So the number of OFDM symbols will go on increasing based on the numerology parameter. So if the subcarrier spacing increases, right? So for 2 power 1, okay, you will see double the number of OFDM symbols, right? Then 2 square, 2 cube, 2 power 4. So if the numerology goes on increasing, ultimately you will see large number of OFDM symbols packed into a single frame, right? Then with this idea, let us get into the 5G use cases. So we very well know 5G standards are actually dictated by a global body called 3GPP, Third Generation Project Partnership. So who are all the members of 3GPP? Original equipment manufacturers, OEMs, service providers, right? Then R&D organizations across the globe, right? So they are all part of 3GPP, right? So all these standards are actually drafted with the help of inputs taken from all these stakeholders. Then people like IMD 2020, they have actually come up with the 5G use cases. So to name, so there are three major use cases. First one, EMBB, Enhanced Mobile Broadband. So EMBB stands for Enhanced Mobile Broadband. Okay, what is the idea behind EMBB? Right? So from 4G, right, when 5G was actually released, the expectation was to have a downlink data rate of 100 Mbps per user. If you look at this data rate actually matches the data rate of a broadband connectivity. This is just like taking a broadband cable and directly plugging it into the mobile. So this data rate ultimately matches the broadband data rate. So that is the prime expectation out of 5G. Okay, the data rate should be able to match the data rate what users are actually getting in the broadband. That is why they call it as mobile broadband. And why the term enhanced is actually coming into picture? Previously, people were able to get around 10 Mbps downlink connectivity in 4G, and here the idea is to push it to 100 Mbps. Okay. Then your uplink, they are trying to get it around 10 Mbps. Okay. So this is from the end user point of view. But what about service provider point of view? If you look at the service provider point of view, the downlink data rate was expected to be around 20 Gbps, and uplink it was expected to be 10 Gbps. Okay, this is from service provider's perspective, and this is from the end user's perspective. Okay, right? So this is the first use case of 5G. And what about the second one? Second one is URLLC. This stands for Ultra Reliable Low Latency Communication. As the name suggests, right? So the network should be highly reliable, right? So that the network should be available for 99.999% of the time. Okay, this indicates the network is supposed to have a very minimal downtime. Now, what about latency? We have already discussed this part. So, latency of a 5G network is expected to be 1 millisecond, right? So, that for applications which are time critical, right? So, this vertical is actually so crucial. Then, apart from that, even though we say the latency is supposed to be 1 millisecond, now in reality, what people were able to achieve is around only 4 milliseconds. People are actually trying to bring it all the way down to 1 millisecond. Then, what is the third use case? The third use case is MMTC, Massive Machine Rate Communication. Or what is the actual constraint behind MMTC? See, MMTC is actually the other name given for massive IoT. Here, people are willing to provide access for number of IoT devices, right? So, if you look at the connection density, they wanted to push the connection density way beyond 10 power 6, right? The connection density is expected to reach around 10 power 6 devices per kilometer square. So what is the idea here? If you have a geographical area spanning for 1 square kilometer, okay, so 5G should be in a position to support 1 million IoT devices. Okay, this is still a far way to be achieved. And in market now you can see 5G red cap devices, where you can directly insert a 5G SIM card into the embedded board and you can enjoy the connectivity for pushing your data from sensors to cloud. Right? Then what about the battery life? The battery life for IoT devices under 5G red cap is expected to be close to 10 years. It is still a far way to be achieved. Right? So with this, we'll move on to the implementation of a 5G core and RAN with the help of open source frameworks. So how can you explore a real-time 5G network with the help of open source frameworks? So if you take a 5G cellular network architecture, right? So you'll have a mobile phone. I call it as user equipment. So this user equipment will be equipped with a kind of SIM card. It could be USIM or ISIM. And this UE communicates with a G node B, right? So this is a G and B, G node B, next generation node B, right? So this is what we refer as access network. And G node B in turn, it is connected to core network. And the connection between G node B and core, we call it as transport network. So this is basically a wireless interface, and this is basically a wired interface, probably an optical fiber connection. Right? This is the optical fiber connectivity. See, this G node B can be further subdivided into one remote radio head, or we can call it as remote radio unit. So this radio unit will feature couple of antennas. So let me consider 4x4 MIMO antennas that are available on a G node B. This remote radio head in turn will be connected to a baseband unit, BBU, and this baseband unit in turn is connected to the core. This is the actual architecture of a G node B. G node B will have couple of antennas connected to RRU or RRH. This in turn is connected to a baseband unit. Baseband unit is connected to the core. In core, you will see large number of elements like AMF, access and mobility management function. This takes care of your control plane, and user plane data is carried out. It is actually taken care by UPF. Apart from this, you will see large number of entities like authentication server function, network repository function, right? Then network slice selection function, session management function, then policy control function, right? So all these entities are. Apart from this, you will also see unified data management, UDR, okay, and the subscriber information will be stored in a MongoDB, right? So if you want to explore all these things, right, what you can do, this wireless environment can be emulated on a single system. So you can use large number of open source frameworks like UE Ransing or SRS Band project, along with Open5GS, Go, if you want to study a complete end-to-end 5G network. Or if you are still interested, you can also look at Aether 5G on RAM. So this is a software defined core. This is the software defined network. So these are all open source frameworks that are available to study the performance of a end-to-end 5G network by emulating the air interface. So this could be used for exploring all the YAML files related to AMF, UPF, ASF. You can also look at the configuration files for GNOP and UE. So all these YAML files can be configured. Then we can also use Wireshark to capture and study the packets, right? You know the format, right? PCAP and PCAP-NG. You can capture the packet and you can analyze all these protocols, right? For example, the protocol between your GNOB and core will be is actually NGAP, next generation application protocol. You can capture the packets and you can apply a filter. You can very well see 5G registration request coming from your GNOB and whether this request is approved or not. All these things can be interpreted from the captured PCAP. Okay, so thank you for your time.